Hi, in this session, we'll be talking about Newton's laws of motion. Okay, so we have here the outline for this chapter. So we have forces and mass, then the laws of motion, then the nature of forces, weights, and normal forces. But first, we must define what is force and mass. Okay, so basically when we talk about force, it is a push or pull. So force is a vector quantity, hence it has magnitude and direction. So in this photo, you have here a man pulling a sled. You have here force applied on a sled, and of course the sled would have to move. Okay, while mass, it is a measure of inertia, where it is how hard the object would change its velocity. So mass is related to the quantity of matter. So the greater the mass, of course, meaning to say that the quantity of matter is also great. So you have here the typical masses in kilograms presented in the table. Okay, then talking about the first law of motion. So the first law of motion talks about law of inertia. So in this law, we may try to imagine an object rolling along or moving along straight line. So if there's no force acting or external force acting on that object moving along straight line, it will never stop. However, if there is a force applied or an external force, for example friction, that object will change its direction of motion or it will stop. So that's what we call as the law of inertia. Okay, so an object moving along straight line will continually moving along straight line unless acted by net external force. That is basically what is the first law of motion all about, or also known as what we call as law of inertia. Okay, so whenever you wanted to change the velocity of the object, so you have to apply what we call as net force. Okay, so in this case, we may also try to consider the reference frame, which is basically we call as inertial reference frame. So inertial reference frame, these are reference frames which are not accelerating. So if the system or the frame of reference is accelerating, then it must not be, it must make the laws of motion of Newton to be invalid. Okay, so the second law of motion talks about forces. Force. So in this figure, you can see a spring balance. So the first balance, it has no weight, so the force applied, of course, is 0. But if you're going to place a weight on the spring balance, of course, it will record a magnitude of the force. As you increase the weights, of course, the force that will be recorded in the spring balance will also be twice as much. So with that, if you're going to relate that one to acceleration, the more you apply force on an object, the more it accelerates. Which means that if you want to accelerate an object faster or more, then you have to apply more force in relation to its mass. Okay, so the massive the object is, the greater force that you have to apply for that object to accelerate faster. Okay, so in this illustration, so you have here for the first figure, the acceleration is quite big relative to the second figure. Okay, the first figure, it has only one object being pulled. Okay, so The second figure, so you have the two objects being pulled by the same force, but the acceleration is half of the first. So with that, we may mathematically state that acceleration of the object is directly related to the force applied on the object, but inversely related with the mass of the object. That is why heavy objects are harder to stop or harder to move. For you to move a heavier object, you have to apply more force. So this is the original, actually this is the original equation of the second law of motion, but we are more familiar with this equation, which is F is equal to ma. But if we are going to deal with the physicality of the equation, this should be the one. Why? Because although they are mathematically correct, but in physical sense, acceleration is a byproduct or the aftermath of the application of the force. Okay, just like in an engine, with a car. The car moves or the car accelerates because of the force coming from the engine. So this one basically is the dependent variable. This one is the independent variables. Okay, so you have there. So we have the unit of forces. So for the SI system, so we have here Newton. For the CGS system, we have here dyne. The one dyne is equivalent to centimeter per second squared. And for the British English system of measurement, so you have here pound, meaning to say pound is a unit of force which is equivalent to feet per second squared times slugs. Okay, so you have here mass times acceleration. So for the dyne, that is equivalent to 1 gram centimeter per second squared, where Newton is equivalent to 1 kilogram meter per second squared. So you have here the conversion factor, so just note of it. Okay, so typical forces in Newton, so we have here the corresponding magnitude of different how do you call objects with their approximation of forces. Okay, so you have here in the second law of Newton, it is very important for us to understand the concept of free diagram. So the free body diagram will show us the sketch of the forces acting on the object. So if you have a particular system, you have to isolate that one that will be considered as our object of interest. Then we are going to superimpose that one in our convenient coordinate system. So in our case, we'll be using Cartesian coordinate system. And of course, since there are forces present on it, we have to apply the concept or the idea of trigonometry and of course algebra. Okay, then apply the Newton's laws of motion, particularly the second law. So an example of the free body diagram, so you have here a book. Okay, the book is of course lying in the palm of the person. So we all know that the book has weight, and the weight is due to the gravity. Okay, so bear in mind that weight is a force. So weight is equal to mass times the acceleration due to gravity. You have to remember that. Okay, so the weight is always going downward. It is plotted along y-axis. And then the force going upward, this is actually the force exerted by the hand of the person going upward, so that the system itself is considered to be in equilibrium state. Okay, so this one is not moving. In this case, the the summation of forces is equal to 0. Okay, and of course you have to draw the free body to superimpose this one in the Cartesian coordinate system. Okay, so you don't bother yourself in this figure, don't bother yourself regarding with the forces acting along y, because there is no forces acting along y in the figure. Okay, that is an example of free body diagram. And if you're going to look at this figure, so there is a force going downward, there is a force going upward, and these forces actually act on the book. And with this, we may have the third law of motion, which is what we call as the paired reaction. So it states that for every action there is equivalent reaction. Okay, so yeah, there in this figure. So if you're going to look at the vehicle, so there is a force that allows the vehicle or the car to move forward. Okay, and at the same time there is a drag force which may be due to friction. So you have there. Then the person pushing a refrigerator. So as the person pushes the refrigerator pushes back to the person. So you have here the free body diagram. Okay, so that's what we call as the action-reaction pairs. And these two, they occur at the same time. The action and the reaction pairs of forces occurs at the same time. Then you have here the exaggerated size of Earth. I mean, yeah, in the small scale. So you have here the maybe this is airplane. The airplane is being dragged by the Earth downward, and of course the Earth is being dragged by the plane going upward. However, the Earth doesn't necessarily accelerate upward because Earth is comparatively bigger compared to the airplane. So in this case, the airplane is very small. So with that, the airplane has the ability, or will be the one to accelerate downward as it is being, if it is being pulled by the Earth, considering that there are no forces acting on the other forces acting on the airplane. Okay, so that's action reaction, and this one is example of long range forces. Okay, so in the fourth example, so you have here a frictionless system. Okay, so the same through, it shows action reaction pairs. That's the third law of motion. So we have here another example. So the push. Okay, so forces actually can be one-dimensional or it can be two-dimensional. So when we talk about one-dimensional forces, it can either be along x only or along y. However, there are forces that can be superimposed in the Cartesian coordinate, which will give you two-dimensional forces, or you have there what we call as the components. So in this figure, the first figure, so you have a physical picture. So the physical picture actually tells you that there are two persons applying force on the object in the space. Okay, so you have there, you have to draw, you have to know the direction of the forces being applied, and we can see that one if we are going to use the free body diagram. So in this case, there are two forces, and of course there should be an effect of these forces on the motion of the object. So you have here in this figure, you can see that there is what we call as a resultant force, which is a byproduct of F1 and F2. Okay, and this is what we call as component. I mean, yes, summation of forces, and you have here the what we call as um, resultant force. And in this case, you really have to use the idea of trigonometry. So you have here the idea of trigonometry. So you should not evade yourself out from the mathematics in physics, because in physics, uh, it is paired with mathematics to see the beauty of the nature. Okay, so earlier we talked about weight. Okay, so the formula of weight was given earlier, and it is equivalent to denoted with W, which is equal to mass times the gravitational acceleration. And bear in mind that the weight is always going downward. It is a vector quantity always going downward. So if you have here the x and y axis, it is along negative y axis direction. Okay, and of course the unit of weight is in terms of Newton. Okay, so you have here the weight of the person. So you will notice if you are in an elevator, if the elevator will go downward and accelerate downwards with the same acceleration of the gravity, a gravitational acceleration I mean, so you're going to feel what we call as weightlessness. Okay, because you have the same acceleration with the acceleration due to gravity. However, if the elevator will accelerate upward twice as much as the acceleration due to gravity, then you will feel uh, the weight. Okay, so it will be twice as much as your weight under normal conditions, or having the acceleration to be 9.8 meters per second squared going downward. Okay, so other forces, so that's the weight, that was weight. Then we have normal force. So when we talk about normal force, these are forces exerted by the surface on the object resting on the surface. Okay, so you have here the first figure. This is this is canned goods. Okay, you're resting on the floor, and you notice that of course there is a weight going downward. But in reaction to that, according to the third law of Newton, that there should be a reaction. Okay, of course, to support the object not to fall, of course, the surface will have to exert force, and we call that one as normal force. And if you're going to superimpose that one in the Cartesian coordinate system, so you'll notice that you have this photo. Okay, so this one actually basically is our Cartesian coordinate system. So you have x, then you have here y axis. So in this picture, the forces acting on the canned goods is along y only, so there is no x forces influenced. Okay, so the second photo, so you have here bag or luggage is being pulled at certain angle. So you will notice that there is force which is basically in two-dimensional perspective. Okay, so the weight is going downward. Okay, so you have here the luggage, so the force applied, the weight and normal force supporting the luggage going upward. So if you're going to draw that one, the Cartesian coordinate system, so you have here this. So the weight is going downward, normal force is going upward. Notice that the applied force is at certain angle theta. So with that, you can decompose that one into its components. Then you are going to apply the trigonometric identities so that you can have the forces along x and along y. So you don't have to deal with this force which is at certain angle. So with that, you can now take the sum of forces along x or along y. That is for the normal forces. For this one, this is a quite complicated photo or presentation because there are more forces now. So you have the influence of two person acting on certain object. So you have the forces. F1, F2, these are applied forces by this person. Then you have the weight and of course the normal force. Notice that the normal force is quite increasing because there is influence of these two person. This one and this one. They have the influence. Okay? Since the object is not accelerating, so the object is still stationary, so the downward force must be counterbalanced by the upward force. And that is the normal force. If you're going to take the sum of these forces, downward forces, that must be equal to the force upward, which is equivalent to normal force. Okay, that is for the free body diagram. And this one, there are cases that we really have to rotate the axis. Okay, so in this figure, you will notice that the surface is inclined. So you have here the normal force exerted by the ground on the person. So it is going to this direction, if you notice, while the weight is going to this direction. Okay, so maybe they are at certain angle theta. So that's the thing that we are going to resolve, because the weight actually, it should be how do you call this one, which should be decomposed into components. Okay, so how are we going to decompose that? Of course, we have to apply the concept of trigonometry. Okay, so review. So force is a push or a pull applied on an object. Then mass, it is the measure of inertia. Okay, the greater the mass, the more difficult you are going to accelerate an object. So with that, you have to apply a large amount of force. Then the first law of Newton states that an object forever at rest unless acted upon by net force, or an object in motion will be in motion forever unless acted upon by net external force. Then in the first law, it is very important to consider the frame of reference, which is basically inertial. Therefore, acceleration is equal to 0. And you have here the second law of Newton. Sum of force is equal to ma, or A is equal to net force over m. Then, important thing that we have to consider is the free body diagram. Third law of motion. For every action there is equal but opposite reaction, and bear in mind that these two are actually occurring at the same time. Then the forces, the contact forces and the long range forces. Then the nature of force, which is vectors in nature. That is why it's very important for us to have the free body diagram, and of course decomposition of forces if that is in two-dimensional. Then weight, which is a gravitational force. You have there the acceleration, the normal force, and the rest. So that is all for this session. Okay, so next session we'll be having more on problem solving. So stay tuned with the next videos that I will be presenting.